Hello, and thank you for joining today's webinar. I'll start by introducing Citrine Informatics, who we are and what we do. I'm then going to discuss what are the challenges you're facing in incorporating recycled plastic feedstocks into products. I'll then discuss how Citrine can help with those challenges, then we'll illustrate that using some case studies and demonstration of how that works in our software. Citrine Informatics provides AI software to accelerate product development, optimize production, and increase sales in the materials and chemicals industry. Citrine's AI platform empowers product experts with no data science background or coding experience to leverage cutting-edge AI that is specifically designed to work on the small and sparse datasets typically found in the materials and chemicals industry. Citrine was founded back in 2013 in the Bay Area, Redwood City, California, but now we have a presence globally. Something we frequently hear from our customers is that in order to keep up with their customers' demands and regulatory changes, they're having to move faster than they ever have before, but with fewer resources. Adapting to all these changes requires exploring a lot of options, but you can't test everything. Lab tests, experiments, they're expensive and time-consuming. And this is where AI comes in. With AI, you can explore a lot of options. You still have to take things to the lab to do real-world experiments, but you're selecting those experiments from a much bigger pool of options that you've explored using AI. And I think this is captured really well in this quote on the right-hand side from one of our users. It says, in learning this field, we're always told that while our goals are faster, better, cheaper, we'll only ever be able to get two of the three. With ML, there is now potential to get all three. To give you a sense of the type of customers that Citrine works with, it's really broad. And it's broad both in the size of the company, from Fortune 50 global companies down to early stage startups, but it's also broad in the materials class or chemistry that those companies focus on. So we work with 6 of the top 10 global specialty chemical companies, 4 of the top 10 global adhesives and sealants companies, 2 of the top 10 global personal care companies. Most of the companies we work with don't want to be named publicly, but a few of those that do are listed here on the left. What results are customers achieving using the Citrine platform? Here are a few examples. A major producer of thermoplastic resins was able to replace 90% of the fossil-derived polymer in a plastic product with bio-based polymer, and in less than 50% of the planned time. That is a huge acceleration. A medical device manufacturer used the Citrine platform to optimize the product cost and CO2 footprint of a product. And they calculated that using Citrine enabled them to reduce the development time by 50 to 60%. Thirdly, a global materials leader used the Citrine platform to lightweight key products while maintaining cost and performance of those products. And they've generated significant value from the decreased time to market and cost reduction. Let's talk about the challenges faced in incorporating recycled feedstocks into polymeric products. It's not easy. It could be a large batch-to-batch variation in the recycled material. There can be a range of molecular weights and densities. There can be contaminants or other polymers mixed in, dyes and aluminum foil from packaging, various additives and fillers. All of this makes it really hard to make a consistent product that meets the customer's requirements. And this is even harder when we're working in an area that has stringent regulations or requirements like food-grade applications. So how can AI help? On the chemical recycling side, AI can help by optimizing the chemical recycling process, so ultimately leading to it to be more efficient and to higher yields. And in a few minutes, my colleague Mark is going to walk you through an example of using our software to optimize a solvolysis process. In mechanical recycling, AI can be used to adapt to the batch-to-batch variability that makes it so hard to make a consistent product. So I'll walk through a case study at the end of our presentation of how you can use AI to formulate products that take into account that batch-to-batch variability in the feedstock while still keeping a consistent product that's in spec.
Citrine Platform has a simple workflow that starts with dragging and dropping your test data into the platform as an Excel file. Then, using no code at all, you can use that data to train an AI model that predicts the key properties of your materials. You can even build your expert knowledge into those models just by teaching the model like you would a human using natural language. Once you have that model, you can use it to test ideas in silico. So if you have an idea for a formulation that you think is promising or a change to a formulation, you just punch that into the model, and it'll quickly give you a prediction that helps you sanity check that idea. The search space is where you set constraints on your materials or formulations that make sure that the candidates that the platform is suggesting are feasible both from a technical and from a business perspective. Finally, candidates is where you tell the platform what the targets are for the key properties of your material. It then returns to you candidate materials that are entirely new, that have a high probability of satisfying those targets. So then you look through those and you select some which are safe bets, some which are more exploratory. You take them to the lab to test them, and then you can put those results back into the data set to train that AI model, make your AI model smarter for the next go around.
Enough of me talking. Now I'm going to hand over to Mark to show you an example using the Citrine platform of how you can optimize a chemical recycling process.
Thanks for that introduction, Steve. Really appreciate it. So now how do we get started? We know exploring optimization of these mixed recycled plastic wastes can be incredibly challenging. But let's see how we can use the Citrine platform to accelerate and optimize those workflows. So let's imagine I'm trying to optimize this process right now, and I'm trying to use Citrine to do so. What does that look like in real time? I can see here that my colleagues have already started some work in exploring these systems. But I want to understand, how do I build it from the ground up? I'm not an expert in data science. I don't have years of coding experience. I've just been hard at work gathering data in the lab. How do I get up and running? Step one is to try and get this data on the platform through the data manager. Now, I can see step one, taking my data in an Excel spreadsheet, dragging and dropping it onto the platform. I can get up and running quickly. So I don't need to spend a lot of time learning how to code, downloading and installing virtual environments, working back and forth. I can take my data as it is, drag and drop it, and I can be up and running on the platform. So that's perfect. Step one, I've got my hard-earned data within the system. What does it look like when it's on the platform? How can I understand what I have, maybe gain some insights from that, and get to work on thinking, what's the next best step? How do I get started working to optimize this system? So let's take a peek at what this data looks like. I know that trying to optimize these systems can be incredibly complex between the mixtures of materials, the inputs, the outputs, and the processing conditions all together. So I need to make sure that the system can understand the complexity that I'm dealing with so that I can accurately model it to help me pick the next best thing to do to be as efficient as possible. So here's a representation of the process and the data that I've been hard at work gathering in the lab. As we can see, it's relatively complex, multiple steps mixing together different input materials, solvents, anti-solvents, catalysts, and ultimately extracting the outputs that I'm trying to optimize. How much of this recycled material am I gathering? So I can think about modeling my process, starting where I start and end where I end. And the platform's done a good job of representing my system. I can see this and it intuitively makes sense based on what I'm performing on a day-to-day basis. And when I look at the end here, what I'm trying to optimize are the things that matter most to me and my business. It's the yield of the different components that I'm trying to extract from this process. So not just focusing on modeling intermediate properties that are going to help build some understanding, but really building something that's going to help me direct what do I do to hit the target goals that are going to tell me if my process can be successful or not. So optimizing the yields of my different components, optimizing the cycle time to make sure that I can accomplish this in a reasonable time frame, and doing this all at once, not focusing on any one individual thing. And there's a lot of data that goes into building this history. Different data, different components. We want to see that the platform is adequately understanding what I'm doing here. So for something like toluene, that's not just a name within the platform. We can see that we've been able to include a lot of information about what this material is. So Citrine, again, developed for the chemicals and materials space. Toluene today is similar to toluene as it's going to be in a year or 5 years. We know a lot about these materials, and we can build good fundamental understanding and models from what these chemicals are and what that means for our process. But on top of just looking at those chemicals, we can tack on a lot of additional information that we as experts think might be important. So things like the viscosity of the materials, boiling points, vapor pressure. In this case, dealing with solubility, me and my team do think that things like Hansen solubility parameters could have some impact in the predictability of the system. So the platform gives us a way to stitch this all together, even though we don't know beforehand if we have a clean, simple relationship to predict everything. But we don't need that. We're just bringing to the table what our expertise expects to be relevant, and then we'll build from there. So step one, I was able to drag and drop my data on the platform, and it looks like we've done a pretty good job representing what I'm doing in the lab. And I'm dealing with tens or dozens of data points, not thousands or millions, because all that data is expensive to gather. So now again, I've put my data in the platform. I want to model it, but I'm not an expert in AI modeling. How can I do that? How can I build it? Well, first, I can see what my colleagues have done before me. So I don't need to download and install any special software, just accessing through this platform. What is an AI model? What's it look like? And how can I use it? So I can jump in and look quickly and see what this represents. Now, there's a large amount of information here, but fundamentally, what the platform is able to do is take all of that complexity within my data. Things about which materials I'm mixing together and which amounts, all those properties of toluene and what toluene really is, the fundamental properties of those materials, and stitching it together to help build models using that wealth of information. When we have a small amount of data, we need to squeeze the most information possible out of it to build the most predictive models. Now, for instance, when we included that structure of toluene, the platform understands there's a lot about that molecule that we can extract to use for predictive capability. Things like the number of bonds, the number of acid groups, the number of hydrogen bond donors, the polarizability. This is a lot of information that, as a chemist or an engineer, I think could be relevant to helping predict these properties. And I don't need to go do a lot of extra work bringing it to the table. The platform's already done that for me. There's a whole host of these other properties that I can explore as well. Number of aromatic bond groups, polarizability, et cetera, et cetera. So we could spend some time tweaking this, but for now, I'm collaborating with my colleague who's built this model. So I'm going to see what my colleague has done before and treat this as a baseline. So all of this data, this information, this trickles down to help predict the properties that I care about. Things like the yields of the different components of my system. And this is just the structure of how that data is put together. What inputs affect what outputs? And I can see that graphically. I don't need to work through a coding interface. So this is the inputs and outputs, but how do I know if it's a good model or not? We can explore that a little bit. So here we're seeing a high-level view of predicting each of these properties that I care about. Not just focusing on predicting one yield, one selectivity, one intermediate product, trying to model everything at once, using all of this data that we've been able to pull together to be as effective as possible. So let's dive in a little bit further. I'm trying to predict the caprolactam yield. What does this look like within the platform? And really important to me, I care about knowing and understanding what's going on in my system. It's not just an input and an output, but if I can learn from my data, that can help me define better experiments. So I can see right here, this is definitely not a black box. I can see directly within my data, what are the things that are most predictive of the property of interest. So I can see in this case, for that yield of this caprolactam, the things that seem to be most important are the separation temperature, the cycle time, how long we're running this for, and the binary interaction parameter between the temperature and the stir speed of that interaction step. So those are pretty key, and they make some intuitive sense to me. But also there's some fundamental properties here. Things like the boiling point of the materials, the number of bonds, the average molecular weight within the formulation. So again, some of this is it's a gut check. And as an expert, it allows me to see, okay, my intuition is in line with what this model is extracting. But there's also some learnings here. Maybe I didn't quite expect that the boiling point of my materials could have some impact here. So that could be some learning for me that I could take and go back to designing the next round of experiments. But further than this, not just seeing how this model's performing, we can dive a bit deeper and just see how are each of these features impacting this output. So we can see for this caprolactam yield, as I vary something like the boiling point, an increasing boiling point of the average amount of the increasing boiling point of the materials in my process tends to decrease the yield of my caprolactam. So that's an interesting trend. So it's something that I can, again, learn from my data. Citrine is giving me a way to explore and see things in my data that might not have been visible before. So it's incredibly valuable for me as the expert to continue to use this data and extract the most information from it. Now that I've built these models, I also want to explore a bit and see if I can run some predictions. I don't have all the time in the world to test everything that I might want in the lab, but maybe I can run some virtual experiments here. So let's take a baseline experiment here that we've run before. And what if I modify it a little bit? What if I test a new solvent that I've never used? So in this data previously, we've used dichloromethane as a primary solvent. Let's swap it with something else. So let's add in a new solvent. How about, let's see, something I haven't tested before. Maybe I could test something like benzyl alcohol. Just a shot in the dark. Let's replace that amount of dichloromethane with benzyl alcohol. Again, we want to make sure we don't break any laws of mass balance. So we'll get rid of that one, and then we can run a quick prediction. And see, that only took a couple of seconds, which is really helpful for me because time is really valuable here. This gives me some insight, not just seeing how the models generally vary, but if I have a specific experiment I want to run virtually, only takes me a couple seconds to test it out. And in the same way, I can explore and see if this is really aligning with my intuition. So decreasing the yield of caprolactam, maybe slightly increasing the solvent loss. So maybe this isn't something I wanted to run, but I'm glad that I could explore that. I didn't need to waste my time running that in the lab. So that's really valuable to me. So going back to this workflow, I've been able to pull my data into the platform and build a model here. And then next, I still want to work towards designing what experiment do I do next. Now, maybe I want to pause and think about this a little bit. So maybe I want to explore some new solvents, something that I haven't tested. So maybe I want to learn a little bit from the external literature. So I can use the Catalyst Knowledge Assistant tool to maybe ask what type of solvents might be best suited for nylon 6 plastics recycling. Just asking in natural language, something casual, and using this tool to parse through millions of open source documents focusing on scientific literature. This can, again, spur some ideas, knowing that even though our data is extremely valuable, there's a lot of knowledge in the external literature that might help teach me. So here I'm getting some insights, something that might spur some new ideas and help me decide what experiment should I do next. Maybe I should try some different solvents, some different anti-solvents, and not just providing some data that might be hallucinated, but giving me the direct sources if I want to go check on those. So that's really valuable to me as something that I can use in the middle of my workflows. So that gave me some new ideas. But now I really want to focus in on designing what's the next experiment that I should do. So let's look at these search spaces. So this is something that, as an expert experimentally, this is pretty intuitive to me. I know when I'm designing these experiments, I have to mix together a whole host of materials. The recycled polymers I'm using, the solvents, the anti-solvents, the catalysts, all the different components. And I have a good gauge on what makes sense and what doesn't make sense. If I'm recycling these polymers, I know I wouldn't want to design a total mixture for my batch process that would have 100% catalysts within that mixture. So if I tell our platform, if I tell the system not to look there, it won't look there. I'm glad that I have that level of control, but not just high level, focusing on the individual ingredients here as well. So if there's specific ingredients that I want to explore, this is where I have a lot of control. And not just on the ingredients that I've tested before, but specifically the platform is designed to help me look at new materials, things that I've never explored. So let's look at this. Within this data set, I've only used a handful of solvents. So in this case, dichloromethane was heavily used. but I have some expectation that there might be some solvents that I've never tested before that I really want to dive deep on. So I can include those within the platform and allow the system to explore them. And how can I get good results there? Well, it's because we're not just building models based on the name dichloromethane or cyclohexanone. We're building models based on the fundamental properties of those materials. And so as opposed to thinking about extrapolating to never before tested spaces, it's more thinking about, am I working within this space that might actually be partially explored already? So I could be getting some good ideas with all the data that I have. So I could tell the system, okay, even though I've done a lot of work with dichloromethane, don't give me any more ideas with dichloromethane. But cyclohexanone, I think, is kind of interesting to me. So please only give me ideas that include cyclohexanone or whatever it might be. But this gives me a lot of fine-tune and control over what I'd like to test next. And not just for those ingredients, not just for testing those unexplored materials, but also for my processing conditions. These problems, as we know, for folks who work in the lab, it's not always just the stuff you put together, but how you put it together. Stir speeds, temperatures, pressures, how you run your experiments can be absolutely critical to the results that you achieve. And again, restricting those to the realm of possibility and being able to understand how these different knobs and levers that we have control over, how do those impact the final performance? It's really critical for me as an operator and an expert in running this equipment. I want to make sure that the only results that I'm going to get are within the realm of possibility. I know I wouldn't want to spin faster, agitate my system faster than 500 RPM, so I'm just not going to allow our models to explore there. So this is great from a usability perspective. A lot of fine-tune and control in designing and ensuring that the experiments that I'm suggested to run are those that I'm actually willing to run. And now finally, let's dive into these experimental candidates. This is the goal. This is what I want. I don't want to tell the system, just optimize one simple thing. In this case, I want to achieve a lot of goals. I want to achieve them all at once, and I want to move quickly. I don't want to optimize one thing and then go back and fix another one. I want this system to help me do everything all at once. So in this case, I'm asking my data to learn and give me the suggested next experiments to try and maximize the yields of all these individual components while also minimizing that solvent loss, minimizing potentially energy usage or cost. Whatever we might want to explore, the system is built to deal with multiple objectives. Typically 5 to 15 is on par with what we see folks using this platform for. And the result here is a statistically ranked list of candidate experiments with a likelihood of achieving those goals. And what does this look like? The output here is an actionable experiment. I can take this and I can go back to my facilities and I can choose to run this right now. So this is something where I'm given the entire list of ingredients, the components, the solvents, the anti-solvents, the individual recycled polymer materials, and I can make the decision to go run this as I'd like. And the goals that I'm attempting to achieve, I'm going to be able to see the likelihood of achieving all of those goals based on the predictive capability and the uncertainties of my models. So this is a really powerful tool to put in the hands of the scientist, not just suggesting the input materials, but also the input parameters, those temperatures, pressures, mixing speeds, because we were able to build a model that encompassed all of the inputs and all of the outputs. The model started where I started and ended where I ended. Then the suggested experiments are going to cover the entirety of that space. And maybe I'll take this to my colleagues down the hall and ask them if it's worth running, or maybe if I have the bandwidth, I'll just go run it this afternoon. But this seems pretty exciting to me. So now let me just pause and recap. What were we able to do? We were able to take in a complex but small data set of data where we've explored using solvent-based processes to recycle plastic materials. We built AI models in our user interface. I didn't have to write a line of code. I collaborated with my colleagues in building these models. We focused those models in a search space into domains that we knew as experts were relevant. We didn't explore things that would be ridiculous or out of the ordinary. And all of that information, that data, that knowledge that we put into this system, looking at new materials we've never tested before, that combined to give us actionable experiments that are statistically optimized to achieve the goals that we care about right now. So now my team, knowing that we've taken that data and that knowledge to focus the next best experiment to do, we can go run that. And once we get the results of that experiment, feed that back into this workflow, have those models improve, and run the next round of experiments. So when we're always using the entirety of our data and our knowledge to make every decision, that's where these efforts really compound, accelerate, and lead to faster and better results. So with that, I'll pause and pass it back to my colleague. And thank you for your time and attention.
Thanks, Mark. Now that Mark walked us through how you can use AI to optimize a chemical recycling process, I'm going to walk you through how you can use AI to adapt to the batch-to-batch variability in feedstocks as often encountered in a mechanical recycling process. Here's the challenge. Your customer wants to incorporate recycled content into their product, which is highly variable, but they still need to meet a narrow set of technical specs. And this is the central challenge that I'll talk about. So how does Citrine help? Let's say you have a batch of recycled feedstock, call it batch A, and you do some characterization on it. Simple things, ash content, melt flow, density, maybe even an IR spectrum. You can then feed the data from that set of tests into the Citrine platform and use a model to give you a prediction of how should I adjust my compound or formulation in order to stay in spec, to get a consistent product, given the properties of that recycled batch. I can then have another batch, and I can do the same thing, adjust the formulation in response to the properties of that batch, maintain a consistent product. If you characterize multiple batches, so you know the general variation or batch to batch from your set of feedstocks, you can formulate a product using Citrine Platform so that it's robust to those variations, so that for the types of variation in feedstocks you're seeing, you should always have a consistent product. We have an example of using this workflow that we've written up into a case study. And that case study is centered on designing hard hats made from ABS plastic, but incorporating recycled content into it. So we are blending recycled and virgin ABS resin with fibers, fillers, and other additives, with the end goal of meeting the customer's requirements. So that's the hardest one here to achieve is the impact strength. So we have a specific target there for the impact strength, with the constraint that we have to incorporate a minimum 20% recycled content. You can find that case study on our website by following this QR code here, along with many other resources about how AI can be applied to both recycling and polymers. Thank you so much for joining us today in this webinar. In summary, the Citrine platform helps you adapt to variable feedstocks, optimize processes, and hit target properties. Citrine platform is easy to adopt, and our team has over a decade of experience rolling AI out across the globe. If you're interested to learn more, please don't hesitate to get in touch. info@citrine.io.